attention. Let me have your attention. We're down to 5,000, so why don't I give 5,000 to all the teams that haven't turned theirs in yet? And let's proceed. Now, location of the roots. What I want you to do, you got your equation? No. Who's got an equation? Who's got a good equation?
Great equation.
Huh?
We have a great equation.
Great equation. David, would you push 3 again, please? That doesn't help any, does it? Okay, there's an equation. It's a quadratic. All of you will have quadratic and f. How do you find the roots of the quadratic? Quadratic equation. Who said that? I did. Good. So you use a quadratic equation. It's equal to minus b plus or minus square root of b squared minus 4ac over 2a. Okay. I want you to find the roots of that equation for quite a few different values of k sub c. Starting at a very small value, going to a very large value. You want me to tell you what you're going to get when you do that?
Root locus.
You're going to get a root locus. If you graph those, root locus is a graph. Let me show you what the root locus is going to look like. Oh, first of all, there's chapter 6 in this book. Control systems analysis and design by the root locus method. That's what we're going for. We're going to design, that's not over the T. We're going to design a control system using the root locus method. So, you can read these if you want to. Here is root locus plots. Oh, by the way, the diagram that I showed you here doesn't have any box in this bottom line. Have you noticed that?
Mm-hmm.
This textbook frequently puts a box in the bottom of it, H, but you can replace that with a 1 and it doesn't change anything. So when I show a block diagram like that, and you can put a 1 box in there if you want to, it doesn't change anything. Anyhow, so there's the formula for the root locus, the closed loop transfer function. If you leave out the H, make it 1, it just doesn't do anything. All right. So here, root locus plots, illustrative, let me see. Talks about angle condition, magnitude condition, talks about illustrative examples. Here's an example. Here's a block diagram that doesn't have an H in the bottom. Here's talks about determining the asymptotes of the root loci. Loci is the plural of locus. You'll actually have 2 roots, so you'll have 2 curves. For the root locus, it's actually root loci, but nobody ever said that. Then determine the breakaway point. Then determine the points where the root loci cross the imaginary axis. And then you do this thing here. And then you choose a test point in the broad neighborhood of the J omega axis and the origin. J is what I call I. You okay with that? If I use I instead of J, will you translate it in your mind? You okay with that? And then draw the root loci. Determine the pair of dominant complex conjugate closed loop poles such that the damping ratio is zeta is 0.5. Don't you love that? Did I say that sentence too fast? Oh, look at this one. Oh, look at this one. Oh, let me tell you about this. I'm going to do something. I'm going to do something here. Well, here's general rules for constructing the root locus blocks. This is on page 283. Locate the poles and zeros. Determine the root locus. Bosh. Oh, nobody's mad at me for tearing out pages out of a book.
I made my day.
No, I hate this book.
So, let me give you an alternative. Would you like an alternative?
Should we return that book?
Click here on root locus modeling. And there's the thing that's on there, there's the thing that's on there, there's the thing that's on there. Can you read this okay? Oh, remember zeta equal 0.5 that I showed you in that thing, determine something? Zeta, this is a graph in the time domain. This is time domain. How many of you like time domain better than Laplace domain? Some of you, huh? What up?
I'm going to really raise my hand on this.
There's a time domain graph. This is seconds or minutes or whatever. And here is Y, which is also known as C. And these are different kinds of responses that we can have our system behave like to make our customer happy. This one is called critical damping. It never goes, let's say this is a set point. Starts out here, the set point starts here, set point changes here. Customers are always changing the set point. Customers are just flaky kinds of folks. And they want the temperature in a room to be 72, and then they want it to be 74, and then they want it to be 68. I mean, they're always changing their mind. Or they want something like that. So there's a controller that is designed to give, what did I say? Critical damping. No overshoot over the final steady state value. Here's one that goes over just a tiny bit and comes down and goes out there. That's pretty sweet. Here's one that goes over, comes down, goes up, goes over again, and then settles down. Here's one that goes way over. In fact, it goes 50% over. This is 100% here. That goes 50% over, comes down, comes in. This is 1/4 as high as this. We have a magic name for that one there. It's called quarter decay. Everybody say quarter decay. The reason that's magic is because two guys named Ziegler and Nichols back in 1942, I believe, decided that was what all customers wanted. Maybe, maybe not. Some customers might want this, some might want this, some might want this, some might want this. Customers are all, you got to give them a selection. Now, here is a root locus plot. This is in the Laplace domain, sorry. Not the time domain, this is the Laplace domain. There's, I told you there'd be two curves, didn't I? Because there's two roots. So here's one curve, comes along here, gets to this point, that's the critical damping point. And it goes this way. The other one starts here, goes over here, and goes up. So the top half of this curve and the bottom half of this curve are just the two roots. And in fact, the top half is just the mirror image of this. It's just a plus or minus on the complex term. So we can ignore the bottom. I'm going to ignore the bottom. It doesn't have any information in it that I need. So I'm going to just look at the top. And this is a point that some customers might want, the critical decay point. And there's those other points are in here somewhere. And then this is the ultimate value. How many of you have heard of KC ultimate? That KC is the one that makes this right on the imaginary axis. That means it oscillates forever. And on this side, it means system blows up. If it's a linear system, none of us have linear systems. Our systems don't blow up, but they never settle down if you're over here. This is the good, and this is the bad side. Everybody say, ooh, positive values of the roots, real part of the roots give us bad stuff. Everybody say that. So the real part of the root we want to be what? We want negative real part in order for it to be stable. So how many, every value of K sub C gives you a pair of these data points that you put on here. Every value of KC you plug into that equation that you derived or I gave to you, give you two roots. Sometimes they're both real, in which case they're along this line. Sometimes they're both complex, in which case they're conjugates of each other and they go along here. So how many different values of K do you need to plug in to get this curve? How many different values of KC, how many different values of KC do you need to plug in to get this curve?
5.
Who said 5?
Josh did it first, then I said.
Josh and, is it Tyler?
Yeah.
Josh and Tyler said 5. If you hit more than 5, it'd be good. How many have a number higher than 5? 10. Who said 16, Jerry?
22.
10.
Who said 100? 100? An infinite number to get a smooth curve. But maybe we could settle for 100. But how easy is that? Oh, by the way, let me show you this damping ratio. That was the zeta term. Some people like to use that. I like to use the decay ratio. Critical damping has no decay ratio. The second peak is, there is no peak. There is no second peak. One of them I showed you was 1/500th decay. You can hardly see the second peak. It's 1/500th of the first peak in the time domain. One's 1/10th decay, one's quarter decay. That's the one that Ziegler and Nichols like. And one's no decay.